Hello everyone, my name is Nasa. Today, my colleague and I will present assignment on the technological feasibility and implementation strategy for innovative cargo tracking and management information system in the maritime industry. We will discuss the need for this system, proposed solution, their feasibility, implementation strategy, as well as the benefits and risks involved. Here is the agenda for the presentation. Maritime logistics plays a crucial role in moving over 80% of global trade by volume. However, despite its importance, the industry faces significant challenges, including visibility gaps, resilient on manual process, and fragmented system. This inefficiency can result in port congestion, delays, and increased costs. Furthermore, the sector is under growing pressure from regulatory requirements and sustainability demand, making the need for innovative cargo tracking solutions more urgent than ever. The main issue is fragmentation. Existing cargo tracking systems are disconnected, relying heavily on paper-based process and isolated database. This lack of integration prevents stakeholders from obtaining a reliable view of cargo status. Consequently, port experience congestion schedules become inaccurate and costs rise. The solution must be entirely digital, real-time, and interoperable among all stakeholders. Our research have three main objectives. First, we aim to propose an innovative information system for cargo tracking and management. Second, we will evaluate the system's technological feasibility, measuring that it is realistic and scalable. Third, we plan to design a phased implementation strategy. Ultimately, our goal are to improve visibility through IoT sensors, enhance efficiency through automation and predictive planning, and strengthen decision-making by providing shared, reliable insight across all stakeholders. We propose a next-generation cargo tracking and management system that combines several advanced technology. This system utilizes IoT sensors and AIS satellite data for real-time monitoring, while AI analytics provide predictive insight. Additionally, it features a cloud-native platform for easy data sharing. We can also integrate blockchain technology to ensure secure documentation. Together, these components aim to offer comprehensive visibility and transparency throughout the supply chain.
Hi everyone, my name is Isma. Let us continue. Our first proposal is the Digital Cargo Tracking and Management Platform, or DCTMP. So what is the definition? This is a feature-rich, comprehensive platform designed for large-scale operators. It integrates Internet of Things, blockchain, artificial intelligence, and cloud computing into one unified system. The focus here is on transparency, efficiency, and security, making it ideal for global port and high-volume trade corridor. The DCTMP has five core features. First, IoT-enabled real-time tracking ensure constant visibility of cargo conditions. Second, blockchain provides secure and tamper-proof documentation. Third, AI-driven predictive analytics forecast delays and congestion. Fourth, cloud platform enables seamless data sharing across ports, custom, and shipping line. Finally, mobile access empower all stakeholders with real-time update and notification. So, Our second proposal is a more lightweight modular system designed for smaller operator and regional ports. Unlike proposal 1, it does not include blockchain, making it less costly and easier to adopt. It still leverages Internet of Things for real-time tracking and artificial intelligence for predictive analytics, but its scopes and complexity are more suitable for developing markets or smaller shipping lines. The Internet of Things plus artificial intelligence platform has four main features. First, Internet of Things device like GPS and RFID provide real-time cargo tracking. Second, artificial intelligence-driven predictive analytics anticipate delays, congestion, and disruptions. Third, a centralized cloud database ensures consistent, reliable data across all stakeholders. Finally, dashboard provide role-based insight to ship owner, port operator, freight forwarders, and custom official. So, this is the comparison of system between proposal 1 and proposal 2. To compare both systems, proposal 1, the DCTMP, is comprehensive and feature-rich, but also higher in cost and complexity, making it better suited for large operators. Meanwhile, the proposal 2, the Internet of Things plus Artificial Intelligence platform, is lighter, more affordable, and easier to adopt, particularly for smaller player and regional markets. Both systems are feasible, but the adoption paths depend on the operator's scale, needs, and investment capacity. So, for the next slide, I will explain about technological feasibility. To ensure the proposed system can work in real-world maritime operation, we assess the technological feasibility of five key technologies. These are Internet of Things, blockchains, artificial intelligence, cloud computing, and cybersecurity with hardware integration. Each technology was analyzed for cost, scalability, maturity, adoption level, and security, which together form the feasibility matrix. Internet of Things is already widely used in maritime logistics, making it a proven and scalable technology. Devices like GPS trackers, RFID tags, and smart container provide real-time monitoring of location and cargo condition. A good example is Mayer's smart containers, which track temperature and humidity in transit. This makes IoT a highly feasible and mature technology for global adoption. Blockchain provides secure, tamper-proof documentation, ensuring bills of lading and custom entries cannot be altered. The ThreadLens project by Mayers and IBM proved the technical feasibility of blockchain in maritime logistics, although it struggled with adoption due to limited industry participation. To succeed, blockchain requires consortium governance and broad collaboration among stakeholders. AI and predictive analytics are increasingly used in maritime logistics, from vessel scheduling to predictive maintenance. They can forecast port congestion, improve estimated arrival and departure times, and simulate disruptions. For example, the Port of Rotterdam's digital twin project uses AI to optimize vessel arrival and congestion management. This proves AI is both mature and highly adaptable for cargo tracking system. Cloud computing plays a key role in ensuring scalability and collaboration across global maritime logistics. It allows stakeholders to share data in real time while keeping costs relatively low. Singapore Digital Port illustrate how cloud platform can simplify reporting and save over 100,000 man-hours annually. This demonstrates cloud computing's maturity and efficiency for large-scale adoption. Cybersecurity is critical to protecting sensitive trade and cargo data. The IMO Cyber Risk Management Guideline provide a clear framework for shipping companies. Essential measures include encryption, strict access control, and immutable audit trails. Without strong cybersecurity, stakeholder trust would be impossible, making this the backbone of the digital cargo tracking system. On the hardware side, the system relies on IoT sensors, RFID readers, AIS transponders, and onboard gateway to capture data. Connectivity is provided through satellite broadband while at sea, 4G and 5G near the shore, and Wi-Fi inside the port. Reliable and affordable infrastructure is essential for ensuring that data flows seamlessly across the system, enabling real-time visibility and integration. So that's all from me at this moment. So my click will continue.
Now we go to the next slide. To ensure smooth adoption, we propose a phased implementation strategy. This process moves from design and pilot testing to infrastructure development, system integration, training, and finally large-scale optimization. Throughout all phases, security and compliance must be enforced to build trust and maintain resilience. Now we start with phase 1. Begin with co-design workshop where shipping lines, port authorities, and custom officials work together to define governance and KPIs. A pilot project is then tested at high traffic port. In the phase 2, the required infrastructure is deployed, including IoT sensors, AIS connectivity, and cloud platforms with security embedded from day one. The phase 3 focus on integration, the system with customs, port community system, terminal system, and enterprise solutions using standardized APIs. Where possible, smart contract can support electronic bills of lading. In phase 4, training and adoption strategies ensure smooth transition. Incentive such as a faster clearance or reduced fees can encourage active participation from stakeholders. And then the last phase is about scaling up to regional and national levels supported by AI for predictive optimization and digital twin models for smarter port operation. Across all phases, strict controls must be maintained, including encryption, secure logging, and adherence to IMO's cyber risk management guidelines to ensure trust and compliance. Benefit of the system. The benefit of the system span operational, financials, and strategic dimension. Operationally, IoT and predictive analytics provide real-time visibility, reduce congestion, and improve efficiency. Financially, the system lowers fuel waste, maintenance costs, fraud losses, and demurrage fees while cutting paperwork. Strategically, blockchain provides secure documentation, transparency, build trust, and AI empowers better decision making. Together, these benefits strengthen competitiveness and ensure compliance. There was a challenges and risk mitigation. Implementation, this system comes with challenges. High upfront costs can be addressed with phased investments and public-private partnership. Data security risks require robust encryption and regular cyber audits. Resistance to adoption can be eased, training and incentive. Interoperability issues demand adoption of global data standards, while connectivity challenges can be solved with hybrid communication models. Finally, governance risks highlight the need for consortium-based systems that prevent vendor lock-in. In conclusion, maritime cargo tracking plays a vital role in global trade. Both proposed systems, DCTMP and the IoT, plus AI platform are feasible, thought suit for different scales of adoption. A phased strategy ensures smooth rollout and stakeholder buy-in. The benefits include efficiency, cost saving, security, and longer competitiveness. Looking forward, such system will form the backbone of smart, integrated, and suitable maritime supply chains. That's all from our group. Now I open for a Q&A session. Okay, question. Why should we adopt blockchain if it had adoption issues in the past? For example, trade lanes. So, trade lanes prove blockchain's technical feasibility, but face governance and adoption challenges. The lesson is to implement blockchain through consortium-led governance and open standard, ensuring wider participation and trust.
We have a question for the audience. The question is, how can smaller operators manage high upfront costs? Thank you for the question. My opinion is that for smaller operators, the key is to phase the rollout and start with the most cost-effective, high-impact tools, rather than attempting to digitalize everything at once. They can begin with IoT tracking on their most valuable trade corridor and utilize least GPS or RFID devices. They can avoid the need for expensive data central and quickly gain visibility by pairing these tools with a cloud-based dashboard.
Thank you for the questions. So I repeat again the question. What if connectivity is unreliable at sea or in remote port? Okay, connectivity is always a challenge at sea, but the system can be designed to handle it. Ships use edge gateway that buffer data and apply basic rules locally, like monitoring temperature threshold even when offline. Once the vessel reconnect, the data is compressed, timestamped, and automatically synced. That the store and forward approach. We also prioritize critical events. For example, if a reefer container door is opened unexpectedly, the alert goes out immediately via satellite. Less urgent telemetry, such as fuel consumption logs, can be waited for and backfill later when the ship is in 4G range or port Wi-Fi. The network itself is hybrid: satellite offshore, 4G or 5G near shore, and Wi-Fi inside port. This ensures automatic failover between different links. For operation, even mobile apps are designed with offline workflow. All actions are timestamped and synced once a connection is available. Finally, to protect integrity, everything is encrypted and digitally signed. So even buffered data is trusted. In short, intermittent connectivity doesn't stop the system from working. It just makes it more resilient.
I think that's all from our group. Thank you for your attention. In summary, our paper demonstrates that innovative cargo tracking system, which is powered by IoT, AI, cloud, and blockchain, are both visible and impactful. With the phase of implementation, they can improve efficiency, reduce costs, and strengthen transparency in maritime logistics. We believe this solution will play a key role in building smarter and more sustainable supply chains. Thank you.